Alright, let's look at the uniqueness proof. Right, so in order to do uniqueness, we have to use um, the mean value theorem, which states this. If function f is continuous on a closed interval from a to b, and a differentiable on an open interval from a to b, then there exists a real number c between a and b such that the derivative at that point is equal to this difference quotient. Alright, so remember, if you remember that, let's say derivative tells you about the slope of the tangent line, so you can think of this as, so this guy is the slope of the tangent line, right? And the difference quotient, remember that this is the slope of the secant line, right? So basically what it says is that, between A and B, we can find a point C such that the slope of the tangent line matches the slope of the secant line using, A comma f of A and B comma f of B, right? So let's draw a picture and see if it makes sense, right? So remember that the f is continuous and differentiable, and roughly differential means smooth. Smooth indicates a smoothness of the graph, so you're not going to have any corners, anything like that, right? So you would have to have a graph going through a comma f of a and b comma f of b, and the graph has to be smooth. So I'll just sketch a smooth curve going from this point, so no corners, anything like that, just a smooth curve, right? All right, so what it said is that, let's see, so the difference quotient here indicates the slope of the secant line connecting these 2 points. So I'm going to draw a secant line here. Let's see, secant line is going to look like this. So this is our secant line. Oops, it's kind of curved. So this is our secant line, right? Using these 2 points here and there, right? Then we are looking for a c value so that at that point the slope of the tangent line matches this guy, right? We can actually eyeball such a point, right? So you can see that this is the slope, and we're looking for a slope, so somewhere around here, right? And this is the c value that we're looking for, so that the secant tangent line at that point. So I'm gonna draw a tangent line there. So I'm gonna use a blue here. The tangent line is parallel to the secant line, right? So that's basically what the mean value theorem is telling us. We know that so if function is continuous and differentiable, then we can always find the c value such that the slope of the tangent line at that point matches the slope of the secant line, right? So let's use that to prove uniqueness of the proof, right? So in order to show the uniqueness, probably the easiest way to use the proof by contradiction. Let's assume that there are more than one, and then see if we can get into some kind of trouble, right? So let's suppose that there exists two distinct roots, right? So we're gonna have to name them, let's say C1 and say C2, right? So the roots mean that, before that, just like the first part, the f of x is, 4x to the fifth plus x cubed plus 2x plus 1, right? So so we know that c1 is a root, so you know that f of c1 is equal to 0, and also f of c2 as well, right? Well, actually, it's I'm not very organized. Maybe can I use root a and b? That make a little bit more sense. So I'm going to use root. First root is called a. Second root is called b. So let's do that. A and b. Right. So we know that here f is again polynomial, so it's continuous and differentiable everywhere. So it satisfies the hypotheses of this theorem, right? So we can apply this mean value theorem. So let's see. I will just say f is note f is continuous and differentiable everywhere, right? So by applying this mean value theorem, we know that there exists, by mean value theorem, there exists some c, right, between a and b, right, such that f prime of c is equal to, alright, so remember that this difference quotient, but we pick a and b specifically so that it's actually, those are roots. So f of a is 0, f of b is 0. So this difference quotient is basically 0 minus 0 over whatever b is and minus whatever a is. So this is actually just 0, right? So what the mean value theorem tells us is that there exists a real number c, so that the derivative is equal to 0, right? Can this give us a proof? A contradiction. All right, so let's look at the derivative. Since we have a function, we can find a derivative, right? Derivative of, let's see, 4x to the fifth, so 5 times 4 is 20, x to the fourth power, subtract 1 from the power, and put 3 in front, x, subtract 1 from the power, so it's squared, and then you have plus 2, derivative of 2x is 2, derivative of 1 is 0, right? So this is the derivative of f of x, right? Notice that this has even power, so this is never negative, and this guy is the same thing. This is never negative, so maybe I should indicate that. So this guy is never negative, which means that the greater than equal to 0. So this is also greater than equal to 0. Now you're adding positive number 2. So we know that this guy is always greater than or equal to 2, right? Which is a contradiction, because we just said that there's going to be a value c such that derivative becomes 0. But if you look at the formula, that can never happen, because the derivative is actually at least 2. So it's got to be bigger or equal to 2, right? So this is a contradiction. So I'll just say this is my lazy notation for contradiction. So this is a contradiction, because mean value theorem says that we can find a c such that the derivative equal to 0, but if you look at the actual formula, then that can never happen, right? So because we got in trouble, the reason why we got in trouble is that we assumed the wrong thing in the beginning. You can see that here there exist two distinct roots. So if we have two distinct roots, or even more, then we would get into the same trouble. So that means that this assumption in the beginning is false, which means that there can be only one. So therefore, right, there exists, oops, if I can spell it, there exists only one root, right? So combining the first component and the second component, existence proof and the uniqueness proof, we could actually prove that this equation has exactly one real root. All right, that's it. I hope that this was clear.